G'day, Chris here and welcome back to ClickSpring. Much of what we do in the home shop is based upon standard industrial processes that have been scaled down to suit the smaller home shop environment. And so it is with the process that I'd like to cover in this Tools Glorious Tools episode. In the previous TGT episode, I described a compact and versatile vacuum system suitable for working with typical gypsum-based investment when lost wax casting. Gypsum investment is quite easy to remove from a finished casting, and that characteristic often makes it the preferred investment if all other aspects of the casting outcome have been satisfied. But if the nature of the part to be cast is such that greater strength of the investment is required, or if higher metal temperatures must be endured, then the ceramic shell process may be worth considering. In this process, the wax model is coated in multiple layers of ceramic slurry and refractory material, de-waxed and then fired to provide a high quality vitrified mould for metal casting. It's not by any means a simple or fast activity, with many steps to the sequence. And like most foundry work, not for the faint-hearted. There are a lot of hazards and variables to control for a good outcome. But with care, using ceramic shell as the investment can deliver superb results. So first, let's take a look at the pattern. I work almost exclusively with resin-based SLA 3D printed patterns for metal casting. And for this video, I'm going to cast by way of example the case components for the dial indicator project. Each part has some extra volume and features that I've added to the basic print to allow for more convenient de-investment and machining later. The patterns have been scaled at the print stage to accommodate the expected metal shrinkage. I'm going to cast these prints in silicon bronze, and previous testing has indicated a suitable shrinkage allowance to be around 1.6%. Now, for all of the convenience of 3D printed patterns, there is one major drawback. The printed resin tends to expand slightly when heated, which can cause cracking of the mould, and occasionally the breaking off of delicate features. Simply choosing ceramic shell as the investment goes a long way to solving this issue, given its greater strength compared to gypsum investment. But an additional step to help solve this is to print the models hollow, with the thinnest possible wall thickness that'll still permit the object to hold its shape, and then to fill it with wax. This maintains the rigidity of the pattern for handling, while helping to solve the cracking issue. The de-wax sequence is arranged so that the wax is melted from the mould before resin burnout, allowing an internal cavity to form. This gives room for the printed resin to pull back from the investment surface as it breaks down, with less risk of it damaging the mould face as it does so. Filling the model with wax is one of the messier parts of the job. I found simply syringing the hot wax into the prints to be the most straightforward way to get the job done, with masking tape helpful to manage the wax spill. For making the sprues and gates, I've settled on a system of pre-made wax elements. 3D printed moulds make them convenient to make, and each of the wax elements can be brought together as required to meet the needs of whatever it is that I'm casting in metal. In particular, this collection of elements makes it easy to set things up for a reliable bottom-gated mould. In this case, I need a substantial runner from which I can gate the models, a sort of combination riser and vent structure, and of course a pouring basin and sprue to feed metal into the mould. Now, being wax, these items are quite easy to work with and can be cut, reinforced and joined together as required without much effort. In the case of the runner for this pattern, I've joined two sections together to separate the printed components and still have them fit conveniently in the slurry bucket while investing. And then I added a small amount of soft iron wire as an insert to give the join to the sprue some extra strength. It so happens that strengthening the pattern like this is a critical aspect of preparing it to withstand the physical handling involved when applying the ceramic investment. The pattern must be quite rigid, with minimal tendency to flex, to prevent unwanted cracking of the layers of ceramic after they've been applied. A long thin section like the sprue, for example, can be made quite rigid with a slender length of steel rod. The caveat is that each of the reinforcing elements must be placed in such a way as to permit their removal during the de-waxing stage. For more convenient handling of the pattern, I embed an air fitting into the pouring basin and then connect to it with a handle when required. This allows full control over the pattern during the investment process. The wax pattern, of course, on its own is quite light, but as the ceramic accumulates around it to form the mould, it gains considerable mass. The mould in this video will end up at roughly 3 kilograms by the end of the process. So far, the air fitting arrangement has handled that load without issue. The handle pops on and off easily, and the wax elements of the mould are designed to make sure that the mould is stable in both the upright and inverted positions at all stages of the process, but most importantly when placed in the kiln for firing. The handle also serves as a convenient way to hold the mould upright for drying. Okay, so now that we have a pattern, we need to coat it in refractory material. The ceramic shell process requires a refractory slurry that can be thought of as the binding material that sticks to the pattern and ideally has a consistency similar to warm honey. The slurry both bonds with the pattern and holds the refractory sand in place, allowing layers of ceramic to be gradually accumulated around the pattern and ultimately to form a fully layered mould. It consists of a colloidal silica binder into which is suspended refractory flour until a desired viscosity is achieved. In its raw state, the colloidal silica has some defoaming and wetting agents, as well as the drying indicator that gives it that vivid colour. But it pours much like water. So the first step is to prepare the flour that'll transform it into a more useful viscous mix. I've found that blending 2 fused silica flours with zircon flour produces a versatile mix. It results in a slurry that works well for the entire temperature range of the metals that I work with, although 200 mesh silica flour on its own is perfectly fine for most use cases. Now the flour has a tendency to settle quite quickly once mixed with the colloidal silica binder, so a suspension agent is required to slow this down. In this case, bentonite flour serves the role well. If producing a fresh mix, the colloidal silica and the flour are mixed together in roughly the proportion on screen. But in this case, I'm topping up an existing slurry mix. In each case, the process of combining the binder and flour is much the same. With a suitable mixing device activated to suspend the mix, first the binder is added as required, and then the flour is gradually added, making sure that each addition has become wetted before adding more. This continues until the desired viscosity is achieved. It's fairly easy to get a feel for whether it's getting close to the desired viscosity just by observation. Once it's close, the mix can be left to fully wet in for 3 to 4 hours and then tested for viscosity. In this case, a number 5 Zahn cup, timed to roughly 20 seconds until the stream breaks, is what I'd like to see for this slurry mix. I found a slightly more viscous slurry gives excellent detail capture for the first investment layer. For the subsequent layers, I thin the slurry down to something like 12 seconds. Okay, so once the slurry is applied to the pattern, it's usually augmented with various refractory sands to create a solid layer of ceramic. There are several choices of sand available, and 2 commonly used are zircon sand in a fine mesh and a coarser refractory material known as chamotte. Zircon is a hard mineral sand with a natural heat resistance, which makes it perfect for the first metal-facing layers. Depending on the pattern, I generally use zircon sand for up to 5 of the initial layers. Chamotte is a fairly light, coarse material, suitable for the remaining layers. This coarser material functions as a filler to bulk up the mould for greater structural strength and to give it additional thermal mass. Now with resin-printed models, a wetting agent is often required to ensure the first coat of slurry fully adheres to the pattern. I'm using shellac flakes, something like 200 grams, dissolved in 5 litres of denatured alcohol. Once dry, the pattern is ready for the first investment cycle. The investment process benefits greatly from being conducted as a standardised routine to help achieve consistency across all layers. My routine is to first resuspend the slurry and then position it alongside the sand that I'm about to apply, along with a wash bucket and a source of compressed air. The pattern is slowly dipped into the slurry, and a brush serves to help cover any sections missed in the dip. A brush can also help push the slurry into any deeper cavities in the pattern and remove surface bubbles. Occasional soft bursts with compressed air helps to remove the bubbles too. Then, as best as possible, the pattern is kept in continuous motion as the excess slurry drips off and back into the bucket. Once the drips have mostly stopped, the sand is then added by hand, again keeping the model moving to minimise the tendency for the slurry to drip or fold over upon itself as the sand is being added. Once covered in sand, the slurry will stop moving entirely, and the pattern can be put somewhere to dry. In this case, I have a small space underneath my bench, perfect for the job. I tend to leave the first coat to dry for 24 hours. Once the pattern is dry, the excess sand is removed and the process repeated. In between coats, it helps to pre-wet the surface just prior to the next dip to get better adhesion between the layers. I've found simply giving a light spray coating of raw prime coat works well, and it makes sure that I have no issues at all with delamination of the primary layers. Otherwise, the process is the same as the first. Dip in the slurry, wait for stability of the slurry on the pattern surface, and then dust the pattern with refractory sand. Now, I mentioned earlier that the prime coat binder has a dryness indicator, which is the source of the lime green colour. Fully wet is green, but as the material starts to dry, it'll turn a light orange, and after enough time, a pale yellowy white. For subsequent layers, this dryness indicator can help to confirm how well the material is drying, but generally I tend to allow 4 to 5 hours for each subsequent layer to dry. So after that first coat, I can generally get in 2 complete cycles per day from then on. As the coating gets thicker, it tends to take a little longer to dry, so depending on the weather, that occasionally slows the process to a single cycle per day for the final layers. For this particular casting, I found that I get the best surface finish results with 5 layers of zircon sand. Once the initial layers are in place, the mould can be bulked up with chamot. After the first chamot layer has fully dried, a layer of soft iron binding wire works well to add strength to the finished mould. It's especially helpful in resisting expansion cracking during the de-waxing stage. This is followed by 2 more layers of chamot to put the rest of the bulk refractory in place. Once the final chamot layer is dry, the investment process is completed by adding 2 more layers of slurry only. This gives the mould a tidier surface, keeping the chamot from shedding, and it also serves to make the identification of cracks much easier after firing. The total number of dips will vary a little depending on the nature of the part to be cast, but here's a summary of the investment schedule for this particular mould that I use as a general guideline for all. This schedule will give a mould thickness of between 6 and 10 millimetres. Okay, so once the mould has fully dried, the next step is to remove the wax. My kiln is not designed to burn large quantities of wax, so I use a simple baking tray and a torch to do most of the job. The main objective here is to remove as much wax as possible from the mould before it enters the kiln for firing, and without igniting a wax fire. This means taking it slow and setting the torch flame relatively low to keep things sedate. I know the quantity of wax to expect, and the mould doesn't enter the kiln until I can verify that that amount has been removed and that only wax residue remains. The kiln schedule starts at 120 Celsius to first remove the remaining wax residue. Next is a ramp up to 300 Celsius for roughly an hour to start the process of breaking down the printed model. Another ramped to 570 Celsius for an hour or so, and the remainder of the printed elements break down, and the soot residue is starting to disappear. The kiln is then taken to 900 Celsius for 3 hours to bisque fire the mould. After which it's left undisturbed overnight to cool to room temperature. The following morning, if all has gone well, what remains in the kiln should be a solid and well vitrified mould. I quite like this point in the process because after all of the preparation work, the results can now start to be seen. It's also the perfect time to closely inspect the mould for cracks and then patch them as required. The small splash residue that was once on the surface of the wax pouring basin now remains as a fragile rim that can be easily cracked off and discarded. Now, something that immediately stands out about a successful mould is that it has a distinctive sound to it. You can hear and feel that it's a dry, rigid structure with a clear ringing note when struck. Nevertheless, it's still quite common to have small cracks as a result of wax or model expansion. This one is quite fine, but regardless of size, the process to deal with cracks is the same in each case. Apply some sort of surface patch. I generally use ready-mix mortar, applied along the crack and then left to set. Otherwise, the mould looks good to go. To the extent that it can be seen, the interior surface is nice and smooth, and the outside structure all looks as it should. For now, it just needs to be left undisturbed for the patch mortar to set. Once set, the mould is well sealed and ready for preheating in preparation for pouring metal. Silicon bronze is an excellent metal for this sort of casting. It's probably the most user-friendly of the copper alloys in terms of its behaviour when molten. Based upon the weight of the wax pattern, I have a reasonable idea of the quantity of metal required. Once the crucible is charged, it's into the furnace that I described in episode 3 of this Tools Glorious Tools series. A quick preheat of the pyrometer probe tip reduces exposure within the furnace when doing the temperature check later. And in normal circumstances, a light skim of oxides is usually all that's required to prepare the melt, as well as confirmation that the metal is at or approaching the pouring temperature. The ceramic shell has been slowly preheated throughout the day to 900 Celsius, and once in place is ready for the metal to be poured. Breakout of the investment is a tedious part of the process, to be sure, but it's satisfying to see the features of the casting appear as the investment is broken away. The wire reinforcement is not that much of a hindrance to the breakout. It tends to fracture along with the investment and otherwise can be easily clipped with cutters. It's also the perfect time to assess how well the investment was applied, with the layers clearly visible, and a good opportunity to identify any problems that may need correction. As the sprues, gates and risers are separated, they too become a point of inspection to assess the metal flow performance and identify any casting defects. Bright, solid, homogeneous metal like this is exactly what we hope to see at this stage. Much of the investment will break away under hammer and punch, but what remains within recesses and cavities generally requires a little more effort to remove. I've had good results using a small pressure washer. The casting gates can be reduced most easily on the belt sander. and the remains of the ceramic investment can be removed from the surface with small picks and probes, followed by a brass brush. The castings will be machined in a later video, but for now, turning down the base of the riser gives a clearer view of the interior. So after all of that work, here are the castings straight from the brass brush, in what will be their rawest form. The most challenging detail to capture in metal from this design, and what drove me to investigate ceramic shell casting in the first place, are the fine, tapered ridges on the caseback. Yet so completely does ceramic investment capture detail that it faithfully reproduces even the layer artefact from the 3D print. This is the core required section of the casting. The material in red will be machined away in a later video. And here's what a small air bubble looks like when cast in metal. I'll chase this out with a graver later. Otherwise, the surface responds well to a light touch with abrasive paper. It doesn't take much effort at all to remove the print artefacts and reveal the metal underneath. For what I'm calling the case body casting, this is the section that's required, and the red is what will be machined away. Again, the various intersections can be cleared with abrasives or a graver if required, or left as is if the cast surface finish is preferred. The surface finish and sprues are a good starting point to assess a casting, but if there's an underlying and perhaps hidden problem with porosity, it'll certainly be revealed when slicing open the casting. You recall from earlier in the video that the pouring process wasn't mechanically or pressure assisted, which generally implies a limit on the casting wall thickness. For reference, the casting thickness at the thinnest point here is just under 3mm. Now I expect you'll agree that that was a lot of work to get to this point. But for the production of intricate parts that exceed the limitations of gypsum investment, and where a solid, homogeneous metal casting is an essential part of the outcome, this remains one of the better options to consider, especially on a per-part cost basis. The setup costs are not too excessive, especially if it's an augmentation of an already existing kiln and furnace setup. Otherwise, the main running costs are similar to what I experienced with small-scale jewellery casting. For me personally, the main reason to bring this capacity to cast with ceramic shell online is that it's going to allow me to better execute on some future projects that you'll see more of over the coming years. Thanks for watching. I'll see you later.